Hi guys, welcome back to Depth of ML. I am Saloni and now I'm going to solve some of the questions on vector spaces and subspaces and the related topics. So these questions have been picked up from our test series, our AIOTs and our quizzes. So if you guys have already not attempted that and you're planning to attempt them, please watch it after you have attempted those questions. So let's get started, and before this I would recommend that you watch the videos that I've uploaded on the vector space and subspace and all the videos that are there just before this, so that you can understand how to solve the questions better. Okay, so let's get started. So the first question is this set of vectors a basis for R3? Okay, so they have given you three vectors. So these are column vectors and they are asking whether this is a basis for R3. Okay, so first of all, let's talk about what is basis. So basis is basically the set of linearly independent vectors, that are going to span R3 or the subspace or space that they have given. Okay, that span the vector space or subspace. Now here they have given us that the vector space is R3. Okay, so we want to find some set of linearly independent vectors which will span R3. So the next question is, what should be the number of linearly independent vectors? Number of linearly independent vectors that span R3, or in this case this is R3, but this could be any vector space or subspace that have been given. So now what is the number of linearly independent vectors that span the R3? Now what are the number of vectors that are there in the basis? Is basically called the dimension of vector space. Okay, so now we want to understand that how many vectors do I need in R3 to be able to span the whole R3. Okay, so I have talked about this in the lectures, but we know that if R3 is there, then I would need 3 linearly independent vectors to span it. Okay, so for that purpose, what we have to basically find it here is that whether these three vectors are linearly independent or not. So this question, whether this is a basis for R3, gets reduced to, is this set linearly independent or not? Linearly independent, not. Now, how do I find whether these are linearly independent or not? So let's understand how to do that. So I'm assuming that you don't know how to do this, so I'm going to show you from scratch. Okay, so these are the three set of linearly independent vectors, and here we are going to use a concept from system of linear equations to solve that. So we know that Ax is equals to 0. Suppose I have given you a matrix and I'm telling you that I want to find a vector x which gives me this 0. Okay, so now if this x is a non-zero vector, then what it means is that there is a non-trivial solution to the system. Okay, so what it essentially means that the columns of A matrix A are dependent or linearly dependent. I'll call them linearly dependent. So they are linearly dependent. Okay, so I'm going to do a similar setup. What I'll do is I'll assume that this is my matrix where I'll put all these three column vectors. So I'll put 1, -2, -1, 2, -3, 1, 5, -8, 1. Okay, and I will try to find a solution, say a vector which is xyz, such that when I multiply this matrix with this vector, I get 0, 0, 0. Okay. Now I'll try to find the solution to the system. If I find that there is a unique solution to the system, it means that this particular system basically gives me a non-trivial solution. So if x is 0 vector, then we can say that A has linearly independent columns. Linearly independent columns. Why can I say that? I can say that because if this particular equation, right, if this particular matrix, if I multiply it to a non-zero vector and it's giving me some 0 vector, then I say that this particular vector exists in the null space of matrix A. But if I say that the only solution to get a 0 vector such that when I multiply this matrix with this vector is when this vector is a 0 vector, then I know that this is a full rank matrix. When I know this is a full rank matrix, it means that all the columns in this particular matrix are linearly independent. Okay, so I have to only find whether this is going to give me linear, this basically has a non-trivial or a trivial solution. Non-trivial solution is basically a non-zero vector, and trivial solution is a 0 vector. So if this system has a solution which is a trivial solution, then it means that the null space of this particular matrix is empty, right? So it's a full rank matrix. It means all the columns are linearly independent, and hence I'll be able to solve that. So there are multiple ways of doing this. One way is you can find the determinant of this matrix. Determinant. If the determinant comes out to be 0, then you will know that these columns are not linearly independent, they are dependent. So then in that case, this will not be the basis of R3. So you can find linearly whether the determinant is 0 or not. So this is one way. Another way is you can convert it to row reduced echelon form or reduced echelon form, and see if you are getting 3 pivots in this case, because there are 3 columns, right? So if you find 3 pivots, then you know that all these columns are linearly independent. So in RRF, you will say whether you have 3 pivots or not. If you have a matrix which is like n cross n, you will look for n pivots. Fine. So I'll take this matrix and I'll try to reduce it to the reduced echelon form, and I'll see if I have all the pivots in all the columns, then I know that these are linearly independent. Now let's do that. So how will I do this? So first of all, I have to reduce this particular value and this particular value to 0. So to do that, what I'll do is I'll do R2 is equals to R2 plus 2R1. Okay. So because of this, what happens is my row 1 doesn't change at all. My row 1 doesn't change, but this changes. So I'm going to do minus 2 plus 2, that is 0, minus 3 plus 4, that is 1, and minus 8 plus 10, which is 2. Then I will do R3 is equals to R3 plus R1. So I am going to reduce this to 0. So this got reduced to 0. Now I am going to add this 1, 2 is 3, and then 1, 5. Right? So this is 6. Now this is an easy observation over here. You can make that these 2 rows are dependent. Right? So they are same. So you can stop here and you can observe this fact that if you now try to create a 0 over here, you will automatically create a 0 here, right? Because these are multiple of each other. So 0, 1, 2 is equals to or let me say 3 times this vector is actually equal to 0, 3 and 6, right? So these are dependent rows. Now if you have dependent rows in a matrix, then you know that the determinant is going to be 0, right? Or this particular matrix is not going to have a trivial solution to the equation Ax is equals to 0. For your sake of completion, let me do that. I want to create 0 over here. So what I'll do is R3 is equals to R3 plus minus, or say minus 3 times R2. So that basically will give me this matrix. So I'll write the solution here. Let me remove this. So what I'll get is, I'll get 1, 2, 5, 0, 1, 2, and I'll get 0, 0, 0, right? So now you know that this system does not have a trivial solution. Ax is equals to 0 doesn't have trivial solution, right? So if this does not have trivial solution, what it means is that there exists a vector such that when I multiply this with this vector, then it will give me 0, 0, 0. Okay, and why are we doing this? Because we know that the definition of linearly independent vectors, definition of linearly independent vectors, or let me call them Li vectors, that will be easier for me, of Li vectors. So we say that vector v1 to vk, for example. So v1 to vk are linearly independent if and only if there are constants c1 plus vk, c2 v2, sorry, c1 v1 plus c2 v2, c3 v3, and so on, ck vk, they all add up to 0 only if c1 is equals to c2 is equals to c3 is equals to ck is equals to 0. Okay, so this is the definition of linearly independent vectors, that when I take a linear combination of these vectors and I take that combination, the vector that I get, if it's a 0 vector, the only possibility that it's a 0 vector should be when I take these coefficients c1 to ck as 0. If that is the only case, then only the vectors are linearly independent. So we have done the similar thing over here, right? How did we do it? So here I had a column vector, say c1 over here, or let me use a different name over here. So here I had a column vector v1 over here. Here I had v2. Here I had v3. Okay, and I said that I am going to multiply them and add them up with some coefficients, and this should give me the 0 vector. Okay, this is the 0 vector. So what I'm trying to do is I'm saying x into this v1 vector plus y into this v2 vector plus z into this v3 vector. So this is the column picture of multiplication of matrix. If you already don't know it, you can refer Gilbert-Strang. There they have referred 4 ways you can multiply a matrix. This is one of them. So this is just a linear combination of columns of A. Okay, so this is a matrix A and this is some vector x and this is a 0 vector. Okay, so here what we are saying is that I took a linear combination of these vectors and this should add up to 0. Okay, so if this happens only when xyz is a 0, or x is equals to 0, y is equals to 0 and z is equals to 0, or I say that I am multiplying with 0, 0, 0 vector, then only if I get it, then it means that these columns are linearly independent. So that same thing that we have learned in system of linear equations, and I'm kind of assuming that you understand system of linear equations because that is something that we have already studied in school. So if you're not referred that, please refer this and come back to this, you will understand it. So here using the system of linear equations, linear independence, we are able to find whether these columns are linearly independent or not. These column vectors are linearly independent or not, and if they are not linearly independent, they cannot form the basis for the R3, because I need 3 linearly independent vectors to form the basis for R3. But here when I try to do that, I found out that these are not linearly independent. because the determinant of this particular matrix will be 0 first of all. Other thing is that I have a 0 row over here, so this is not a full rank matrix. So you can use rank nullity theorem to find that nullity is going to be 1 for this. It means there exists a vector in the null space of this particular matrix that such that if you take a linear combination of these columns, it will give you a 0 vector, and that particular vector in the null space is not the 0 vector. It's some vector apart from 0 vector. Right? So you are basically adding all these concepts that we have learned in linear algebra to find the solution for this. Okay. So when the question is asked whether this is a basis for R3 or not, you will basically find what will be the dimension of this subspace. Then according to the dimension of the subspace, you will find those many linearly independent vectors. If you are able to find those many linearly independent vectors, you can say that it can form the basis. But if you're not able to do, like here, we were not able to find 3 linearly independent vectors for R3. So we will say that this is not a basis for R3 because they are not linearly independent. Now let's look at this question. So V is a vector space and S is a subset of V. Determine whether S is a subspace of V. Okay. So here we are being asked to determine if this particular set of vectors, which is S, is a subspace of V or not. So in subspaces questions, you will see multiple variants over here. So this is one of the variants where they have not redefined the addition and multiplication operation. Okay. So in a vector space, there are very important things that you should check. So in a vector space, first of all, you should check whether this is a valid subspace or not by checking that the 0 vector exists in this vector space or not. Second thing that you should check is that this is closed under addition or not. Under addition. So if you don't understand what is closed under addition and closed under multiplication, please go and check the other videos. I have explained that there. So whenever we have this kind of questions, you will see that, so in this part, as I was saying, that the addition and multiplication has not been redefined. So good thing about that is that you can assume that the addition and multiplication is same as the original vector space. So this is the standard way of adding and multiplying, as they have not specified it. We will see questions where they redefine it and how we should approach those questions. But in these kind of questions, what you will do is you will end up checking these 3 things, and these 3 things will only tell you whether this is a valid subspace or not. Fine. Now let's start with this. So this is the original subspace, original vector space, which is R3. Fine. So now they have defined a vector space or subspace. They are trying to define a subset. This is, we don't know yet whether this is a subspace or not. They have defined a set of vectors such that they take this form. So they have x coordinate, then 12 and 3x, and x belongs to R. Okay, so this is the real number line. Real numbers, all the real numbers. So R is basically the real numbers. So the way we will approach this is we will check whether these 3 things satisfy. If one of them does not satisfy, this will not be a subspace. So first of all, let's understand what is this set contains. So this set contains vectors like, so let me say x is equals to 1. Okay, so the vector will get is 1, 12 and 3. Okay, now let me say that x is equals to 2. So if x is equals to 2, I'll get 2. Then I'll get 12, and then I'll get 3 into 2, 6. Okay, this is another vector. Then let me take x is, so this is x is equals to 2. Then let me take x is equals to 3. Then I'll have 3, 12 and 3 into 3 is 9. Okay, and so on. So all the vectors will be of this form. Okay, now the first thing that I will usually check whether the 0 vector is present in the vector space or not, or in this set or not. Because if the 0 vector is not present, then we know that this particular set cannot become a subspace. So tell me whether this set will ever contain a 0 vector. The 0 vector obviously will be taken from R3, and R3 0 vector is 0, 0, 0. So you will say whether 0, 0, 0 is present or not. So you can check this very easily. See, the second coordinate is always 12, right? So even if I take x is equals to 0, what will I have is I'll have 0, 12 and 0. We can never have a 0, 0, 0 vector in this set in S, right? Because this second coordinate of this vector is always 12, so you will not have this kind of a vector ever, right? So therefore 0 vector does not belong to 0 does not belong to S, therefore it's not a subspace. Okay, so because the 0 vector is not present, so this particular condition did not get satisfied. So we'll stop here. We don't even have to check the next two conditions, and we can say confidently that this is not a valid subspace. So this is no, because 0 vector does not belong to S. Now let's look at this question. If V1, V2 up to V6 are 6 vectors in R4, which of the following statements is false? So this has been given that there are 6 vectors from R4. So what is the meaning of R4? So R4 means your vectors will look like this. They'll be like X, Y, Z, W. Okay, you will have the vectors of this form. Now they are asking which of the following statements is false. So one of these statements is false, but we will check every statement and see how they are. So it's saying these vectors are not linearly independent. So this is true because in R4, a set of more than 4 vectors will always be linearly dependent. Why? Because R4 is a vector space where you will need 4 vectors, 4 linearly independent vectors to form the basis. If you have the 5th vector in that particular set, then that 5th vector can always be represented using those 4 linearly independent vectors, and hence any vector space or any not vector space, any set which has more than 4 vectors in R4 will always be linearly dependent. Okay, so this is true. Fine. Now let's see the other statement, which is any 4 of these vectors form a basis for R4. So it's saying if I take any 4 of these vectors, it can form a basis for R4. So this is false. So you can't take any 4 vectors to form the basis. You have to take 4 linearly independent vectors to form the basis for R4, and hence this is not true. Okay, so the explanation for this is that we must take 4 linearly independent vectors. We don't know what are these vectors, right? So they have just given us V1 to V6. All I know that these can be the vectors of the form, say V1, 2V1, 3V1, 4V1 and 5V1, right? I don't know what the form of these vectors or 6V1, right? I don't know what is the exact form of these vectors is. So I cannot claim that if I take any 4 of these vectors, it will form the basis for R4. Okay, so we have to take 4 linearly independent vectors, and no such information is given. And no such information, not, or you can say not any 4 vectors. Okay, so this statement is false. So if this is an if this is a MCQ, you can just take and move ahead. But I will recommend that you check the other options also, because sometimes you might get confused in very similar options. So we'll check the C option as well. It is not necessary that these vectors span R4. So this is coming from the explanation of statement B only, that it might not be necessary that they span R4, right? So it can happen that these vectors, for all I know, that these vectors can be of this form, and all they will span is the linear combination of vector V1, right? Hence I don't know. So it is not necessary that this can span the vector space R4, because to span vector space R4 I would need 4 linearly independent vectors, and no such information is given here, so I cannot claim that, and hence this is true. If V1, V3 v4 v6 span R4, then it forms the basis for R4. Okay, so this has been given that these 4 vectors are basically forming the base, they are spanning the whole R4. Okay, so they span R4 and then it forms a basis of R4. So I know I need 4 linearly independent vectors to become the basis of R4, and all these 4 linearly independent vectors will actually span R4, and hence this statement is true. Okay, because if they can span R4, it means, and I need 4 vectors only to span the R4. So these 4 vectors are sufficient to span R4, that it means that they are linearly independent, hence they can form the basis of R4. So I'll just add this explanation over here. If v1, v3, v5 and v6 span R4, it means that they are linearly independent. All are linearly independent. Or let me say this set v1, v3, v5, v6 is linearly independent. Hence they can become the basis for R4. So the correct answer for this question, the statement which is false, is B option. Now let's look at this question. V is a vector space and S is a subset of vector V, of the vector space V. Determine whether S is a subspace of V or not. Okay, so this is similar to the question that we solved just before the last question, that here they have not redefined the addition and multiplication operations. So we can assume that addition and multiplication operations are being inherited from the V vector space, which is R2. Now here, to solve these kind of questions, what you should check is, I'll just rewrite here, you should check whether the 0 vector is there, closed under addition, and closed under multiplication. Okay, so let's start with the 0 vector. So before we start with the 0 vector, let's understand the form of these vectors. So these vectors are of form xy, where 2x minus 5y is equals to 11. Okay, so if I have to write this vector completely in the form of x, how will I write it? So I'll write this is x, and using this equation I can write that 2x minus 11 is equals to 5y, and y is equals to 2x minus 11 by 5. Okay, so here let me put this in this form. So this is the form of my vectors in this particular subset, which is S. Now to find the 0 vector, I will try to make both of these things as 0. So if I want to make this 0, I will take x is equals to 0. So I'll get 0, but here I'll get minus 11 by 5, right? Can I get, maybe I can try setting this 0 and this will become 0. So let me set this as 0. How will this become 0? So this will become 0 only when, so I want to make this as 0. So if x is equals to 55 by 2, this will become 0, but then x, the value on the upper coordinate, will be non-zero, right? So it means that 0 vector, which is 0, 0, this does not belong to S, right? Therefore, it cannot be a subspace. So because 0 vector does not belong to the S, hence this is not a subspace. Fine. So the answer is no, because 0 vector does not belong in S. Fine. Now let's look at this question where we are given, let 0 be this vector. So what is this? This is a 0 vector. Okay, where 0 is a 0 vector belonging to Rn. So it basically can have n coordinates. Okay, which of the following are correct. N coordinate means, so if R2 is equals to, if N is equals to 2 and I'm talking about R2, so let me show you what it means. So if N is equals to 2, it means I'm talking about R2, so my vector will look like 0, 0. If I'm talking about 4, then I'm talking about R4, so my vector will look like 0, 0, 0, 0. Fine. So now we are talking just about the 0 vector. Now it's asking us, now first of all, this Z that they have defined, this Z is a set that consists of 0 vector. Okay, so this is a set consisting only 0 vector. Fine. Now they are asking us which of the following statements are correct. So this is a MSQ type question. So there are multiple options that can be correct. So this is why I have taken this question, is that because many students make a lot of mistakes in this. They don't understand a lot of things about 0 vector space. So to clarify that, I have taken this question, but otherwise it's a very simple question. So the dimension of 0 is 0. Okay. And I've seen students struggling with this particular statement. Okay. So this particular statement is actually true. So we are saying that the dimension of Z is 0. Z is a vector space. It's a 0 vector space basically. So this is 0 and Z is basically a 0 vector space. So let me write it over here. So this is a 0 vector space. Now this 0 vector space is kind of special because first of all, this is spanned by empty set. So we know that in the basis we can only have linearly independent vectors, right? Now 0 vector is dependent by its nature. So 0 vector is always independent, is always a dependent vector, is always a dependent vector. So if your set consists 0 vector, then set will always become a dependent set of vectors. Okay, so 0 is a kind of vector which is always dependent, and in my basis I can only take linearly independent vectors, right? So if I have a 0 vector space, I can't take 0 vector in this, so I say that this is spanned by empty subset, empty set. So the 0 vector space is kind of special. This is spanned by empty set. So if it's being spanned by empty set, it means the number of vectors in the basis of this particular vector space is 0, right? And the number of vectors in the basis of a particular vector space is equals to the dimension. Hence the dimension of this 0 vector space is 0. Okay. The basis for Z is 0 vector in this. Now like I said, 0 is always a dependent vector. So, and in basis we always take linearly independent vectors. Hence this statement is false. Why is this false? Because basis always has linearly independent vectors, but 0 vector is dependent by nature or by definition. Hence this is false because the basis of Z is the empty set. So I'll write it here that basis of 0 vector space is basically the empty set. This is because this is being spanned by empty set, so the basis of 0 vector space is empty set. Z is spanned by 0 vector. Now this is correct. Okay, so in span when we talk about, we don't say that we always want linearly independent vectors, right? To give you an example, say I'm talking about R2. Then I can say that this particular set 0, 1, 1, 0 and say 2, 2. They span R2 and I will be correct. This statement is correct. Now I know that the basis of R2 cannot have more than 2 linearly independent vectors. So this means that this set is linearly dependent. So this particular set is linearly dependent, but that's not required to define. Like that's not something that we can't do for span. So this particular set of vectors is linearly dependent, but they can still span R2. Okay. Hence, this statement that Z is spanned by 0 vector, this is correct. This is true. Because this can span the 0 vector, and in 0 vector space you have all the vector, or there's just one vector 0. If you multiply it with any scalar, you will get 0. If you add 0 vector with a 0 vector, you will get 0, and hence this is spanned by 0 vector. Now Z is a subspace of Rn. Now this is also true. So we know that the 0 vector space should contain 0 vector. So there are 3 conditions. So we should have 0 vector. We should be closed under addition. And we should be closed under multiplication to be a subspace. So if I am a subspace, I should have all these properties. Now let's take the example of 0 vector space. So the 0 vector is present by definition. Now if I add 0 vector with 0 vector, I'll get a 0 vector. So 0 vector always belongs to the vector space, which is the Z vector space. Hence this is closed under addition also. If I, this is closed under multiplication. This is closed under multiplication. Multiplication. So if I take any C that belongs to R and I take C0, then that will be 0, and 0 already belongs to Z. So this is closed under multiplication also. So this is a valid subspace of Rn. Okay, so 0 vector space is a subspace of Rn. Also, the dimension of the 0 vector space is 0 always. The basis for the 0 vector space is an empty set. The Z can be spanned by a 0 vector, and it's a subspace of Rn. Fine. So the options A, C and D are correct. So A, C and D are correct. Let's move on to this question. So this question is taken from our quiz actually, and this is a very simple question, but the reason I have taken this question in this series is because I have seen a lot of students making mistake in this simple question. So let's see how to solve this. So if v1 to vn are linearly independent vectors, the space they span has a dimension dash, and these vectors are a dash for that space. Okay, so there are 2 missing blanks that we have to fill using the options that have been given here. So first of all, let's see this, what information we have. So we have v1 to vn. There are n vectors in total, which are linearly independent. So they are linearly independent vectors. So what do we know about linearly independent vectors? So if I have v1 to vn, that means that I can span a space of dimension n. A space of dimension. So this is going to span a space of dimension n. Okay. So here it makes this C option and D option incorrect because they are saying n minus 1 dimension. We know that it's going to span a dimension which will be of space, it will span a space which will be of dimension n, right? So given that, this means that this is n. Now the second part is these vectors are a dash for that space. So let's see these 2 options, basis and span. So let me try with span first. These vectors are a span for that space. So that's an incorrect statement. Why? So the correct statement would have been vectors span the space. But the statement that has been given to us are these vectors are a span for that space. No. So a vector space is spanned by these vectors, linearly independent vectors, or these set of vectors, but it's not the case that these vectors are a span for that space. The space is spanned by the vectors, it's not the span of the space. Okay, so the correct terminology that we have to use is that the vector space is spanned by these vectors. So given that that terminology is not given, so this option is incorrect. So the correct option is that these vectors are a basis. They are a basis for that space. Basis, because we know that basis has linearly independent set of vectors, Li vectors, that span the space. So these are the set of vectors that are linearly independent. Also, they are spanning the space. Hence, they form the basis for that space. Okay. So this is the correct answer, which is A. Okay. Now let's take a look at this next question, which is again a vector space has been given to you, and a subset of those vectors that are part of the vector space we are given. We have to determine whether S can be qualified as a subspace or not. Okay. So V is in Rn. It means that the vectors that are in V vector space will have n coordinates, and the set of vectors, which is a subset of vectors that have been taken from V, is of this form, where x belongs to Rn, Ax is equals to 2x, where A is a particular n cross n matrix. Okay. So we know that to solve these type of questions, what we have to do is we have to check three things: whether the zero vector belongs to this set, then whether this set is closed under addition, and whether this set is closed under multiplication. And here I should be more specific. It should be scalar multiplication. Okay. I'll come to that. What is the meaning of scalar multiplication? I'll briefly go over that. But let's start with our first point, that whether the zero vector, this set, belongs to S. So this is the question that we have to solve. So how do we determine that? So if zero vector belongs to S, then A0 should be equal to 0. Okay. So if this is the case, then we'll say that this zero vector actually belongs to this set. Now let's take A0. So we know that if we multiply any matrix with the zero vector, it gives us 0, right? But the other way to do this is we have to look at this particular equation that has been given to us. So we are going to write A0 gives us 2, 0. Okay. Here this is x we are taking. So we are basically setting the same form as that has been given to us in the set. Now we know that if you multiply 2 into some zero vector, we'll always get the zero vector. So this basically gives you A0 is nothing but 0. And I had said that if 0 belongs to this, then this will be true. And because this is true, this means that zero vector indeed belongs to S, right? So zero vector belongs to S. So this condition has been checked out. Now we have to check the next two conditions. Okay. So the next two conditions that we are going to check is whether they are closed under addition or not. So this is closed under addition. So what is the meaning of closed under addition? So it means that if x1 belongs to if x1 belongs to S and x2 belongs to S, then x1 plus x2 should also belong to S. So if this condition is true, if this is true, then we will say that this is closed under addition. Okay. If this is true, then closed under addition. So let's see. So I'll assume that x1 and x2 are such vectors that belong to S. Okay. So I know that because these vectors belong to S, then ax1 is equals to 2x1 and also ax2 is equals to 2x2. Okay. Now I want to check whether what will be the, if x1, x2 belongs to S, x1 plus x2 belongs to S, then they should also be of the same form. So let's do that. So let me say that let me check what will I have when I multiply A with this matrix. So I can do the distribution of this multiplication. I can write ax1 plus ax2. Now what is ax1? Ax1 is nothing but 2x1. So I have 2x1 plus 2x2. Now what is this? This is nothing but 2 into x1 plus x2. Okay, so I started with x1 plus x2 and I got the form that was desired. So ax1 plus x2 is giving me 2 into x1 plus x2. Now if this was a vector y, then you can write it as 2y. Okay, so this is of the same form of the vectors that exist in this S. Therefore, this is true. Okay, so this is true. Now this is true. Hence, therefore, this is closed under addition. Fine. Now we have checked 2 out of 3 conditions. So we have checked whether the 0 vector exists. We have also checked whether this is closed under addition or not. Now we have to see whether this is closed under scalar multiplication. Scalar multiplication. So what is the meaning of this? So first of all, we have to see where the scalars are coming from. So C, let this be a scalar. If this is not given in the question, you will also always assume that these are coming from the real number line, or they are real numbers. Okay, so these are real numbers. So if they have not specified where the scalars are coming from, we'll see some questions where they specify where the scalars are coming from. If this is not given, you will always assume they are coming from real numbers. So what is the meaning of closed under scalar multiplication? It means that if x belongs to S, then Cx should also belong to S, where C is coming from the real number line. So all the possible scalars that are coming from the real numbers, if I have x as a vector that belongs to this subset S, then any multiple of that vector should also belong to S. Then only we will say that S is closed under scalar multiplication. Okay, so let's assume that let's assume x1 is a vector that belongs to S. Okay, so if x1 belongs to S, that means that ax1 is actually equal to 2x1. Fine. Now let me see, we will check if Cx1 belongs to S. Okay, so I will say A into C of x1. Okay, so now I know that I can take C out. I can say A of x1. I know what is the value of A of x1, that is equals to C into, so this C will come here. Ax1 is 2x2, right? So this is 2x2. I can just rearrange these a little bit, and what I'll get is 2 into C of x2. Sorry, this is x1 only, it's not x2. This is x1 and this is, I'll rearrange this a bit, so I'll get C into this. Okay, so I had said that, so I started with Cx1 and I got a form of 2 into Cx1. Now if I replace this Cx1 with Z, I'm getting a form in the, I'm getting 2Z, right? So it means that if Cx1 belongs to, if x1 belongs to the set S, then Cx1 also belongs to the set S, right? Therefore, this is closed under addition. So this is true. Therefore, closed under scalar multiplication. I said addition before, but this is scalar multiplication. Okay, so hence we had 3 conditions. All 3 of them checks out. Hence this is a valid subspace. So the answer to this question is yes. All 3 conditions check out. Okay, hence this is a valid subspace. Moving on, let's see this question. So here it has been asked like which of the followings are subspace of R3, and we have to select all that are correct. So this is a MSQ kind of question. So this is MSQ, multiple select question. So multiple answers can be correct, multiple options can be correct from this. So let's see this. So let's start with U. Okay, and we have to do the same thing. We'll check three things: zero vector, whether zero vector is there or not. Then the other thing that we have to check with this is closed under addition. And the third and the final thing that we'll have to check is closed under scalar multiplication. Scalar multiplication. With these three things, we'll be able to find whether these are valid subspaces or not. So let me start with option A over here. So I'll start with A. So you have a set of vectors u is equals to x minus y, x plus y, x minus y, and x and y belong to R. So this is real number. Okay. So let's see this. U is equals to set of vectors such that this is x minus y. This is the whole vector, x plus y, and this is x minus y. So first of all, I'll check whether the zero vector belongs to this. So if x is equals to 0 and y is equals to 0, then I'll have the zero vector, right? Because I'll have 0 minus 0, 0 plus 0, and then I'll have 0 minus 0. So this is giving me a vector of form 0, 0, 0, right? So this belongs to U. Therefore, this is correct. Okay, so zero vector checks out. Now I have to see whether this is closed under addition or not. So how will I check whether this is closed under addition or not? So let me take another color. Closed under addition. Okay, so I'll assume that I have two vectors of the form. So I have v1, which is equals to, I'll write them as column vectors now, which is x1 minus y1. This is x1 plus y1, and this is x1 minus y1. So this is my first vector, and the second vector, let it be v2. We have x2 minus y2, x2 plus y2, and I have x2 minus y2. Okay, this is the form of these vectors. So if v1 and v2 belong to u, then v1 plus v2 should also belong to u. Okay, so I have to check whether v1 plus v2 is of the form that is given over here. So I'll add these two vectors. I'll get x1 minus y1 minus plus x2 minus y2. So I'm showing you this in a very elaborated fashion, but you can do very quickly without even doing these things. You can do these calculations in your head and you will get the answer. So this is x2 minus y. This is 2. Okay. Now I'll just do a little bit of rearranging. So I'll get x1 plus x2 minus y1 plus y2. Then I have x1 plus x2 plus y1 plus y2, and I have x1 plus x2 minus y1 plus y2. Okay, let's assume x1 plus x2 is equals to a and y1 plus y2 is equals to b. So what is the form of the vectors that I'm getting here is I'm getting a minus b, a plus b, and a minus b. So this is the same form as of this vector, right? This is the same form of this vectors. Therefore, this belongs to u. Therefore, this is closed under addition. Closed under addition. Fine. So I've checked this condition. Now let's check for closed under multiplication or not. So if you have to be really sure that all of the conditions are met, you'll have to do it this way. If one of the conditions from these three conditions does not satisfy, you will definitely know that this is not a valid subspace and you can move on to the next option. But because here I have to ensure that this is a valid subspace, I have to check for all three of them. Okay. Now I'll check whether this is closed under scalar multiplication. So how will I do that? So I will say that I have a C that comes from some real number. Okay. So I will say if say V1 is equals to say x minus y, x plus y and x minus y. Okay. So if V1 belongs to U, then V1 C into V1 should also belong to U. Okay. If this satisfies, then we know that this is closed under scalar multiplication. So let's do that. So let me take C into V1. So I'm taking some C which comes from some real number line. I don't know what the value of C. It can be anything from the real numbers. I'll see what is the value of CV1. So what I have to do is I'll have to multiply this C in the inside, which is of this vector form. So this is like this, x plus y and x minus y. Fine. Now this is right, we have to multiply this. So this is cx minus cy, this is cx plus cy, and this is cx minus cy. Now let's assume that cx is equals to a and cy is equals to b. Okay, so if I assume that, I will have a minus b, a plus b, and I have a minus b. Now my vector, this is of the similar form over here, right? This is of the same form. Then this, I know that this definitely belongs to this form of vectors, definitely belong to U. Therefore this is closed under SM, scalar multiplication. Okay, so all the three things checked out here. So this is correct, this is also correct, right? So this option is correct. Now we have to check the other options. So let me take the B option over here. So this is the B option. We have to check whether this is a valid vector space or not. So we have to check for three things: zero vector, closed under addition, and closed under scalar multiplication. Okay, so let's check for the zero vector first of all. So if I take 0, x is equals to 0 and y is equals to 0, what will I get? I'll get 0, 0, and minus 0 is 0, right? So this belongs to V. So this checks out. Now I have to do closed under addition or not. So I'll assume two vectors. I'll say I have x1, y1 and minus y1. And the other vector that I have is x2, y2 and minus y2. So I know that they belong to they belong to V. If they belong to V, then their summation should also belong to V. So I'll just add them up. I'll see whether their addition belongs to V. So I have x1 plus x2, then I have y1 plus y2, and then I have minus y1 minus y2. Now let me say x1 plus x2 is equals to a, y1 plus y2 is equals to b. So if I do this, I'll get a vector of form a, b, and this is nothing but minus b. Okay, now I know this form actually belongs to V. So this is correct. So this also checks out. So let me create the divisions here, so we know which is what is what. So this is for addition. Okay, now I have to check for multiplication. So for that, I should see that if x1, y1, or let me not write x1, so x, y and minus y, they belong to V, then C that comes from R, so for all C that comes from R, C into x, y minus y should belong to V. Okay, so we'll do Cx, so the vector we can just multiply it inside Cy and minus Cy. Okay, now you can again assume that Cx is equals to A, so this is A, this is B, then this will become minus B. So this is of the form that is given to us, hence this belongs to V. So this is closed under scalar multiplication also. So this is also correct. So this is also a valid subspace. Now let's see this part where they have given us this vector space or this supposedly subset, and we have to check whether this is a valid vector space or not. So let me add it here. So this is my C option. So let's see. So we'll do the same things. We'll check for zero vector, addition, closed under addition, and scalar multiplication. Okay, so let's see whether zero vector exists in this. So we'll take x is equals to 0 and y is equals to 0. So if we do that, we'll have 0 square, we have 0, 0 plus 0, which is nothing but 0, 0, 0, which belongs to w. Okay, so this checks out. Now let's do the addition. So let me take x1 square, y1, x1 plus y1 to be the first vector that belongs to w, and then let me take x2 square, y2, x2 plus y2. This also belongs to w. Okay. Let me draw a line here. So let me add them up and see if this is of the same form. So we have x1 square plus x2 square plus y1 plus y2. Now we have x1 plus x2 plus y1 plus y2. Okay. Now let me assume that x1 plus x2 is equals to a and y1 plus y2 is equals to b. Now observe this very carefully. So this is the addition, right? Now here, can I write this particular part? So this is first of all not a plus here. This is a comma. So this is the vector form, right? So can I write x1 square plus x2 square as a square? No, right? So x1 plus x2 whole square. It should have been x1 plus x2 whole square is equals to a square, right? But x1 square plus x2 square is not equal to a square, right? So though if I'm adding this, the form that I'm getting is not of the form that I have here, x square, right? Therefore does not, so this vector does not belong to w. Okay, so this is not closed under addition. Hence C is not a valid vector space or a subspace. So this is not valid. Now let's take the final one and see if this is a subspace or not. Here, so we have the vectors of form x, y, z, where x minus y should be equal to 0. So again we'll check for three things. We'll check for zero vector, we'll check for closed under addition, and we'll also check for closed under scalar multiplication. Closed under scalar multiplication. Okay, so first of all, let's do the first part where we'll take x is equals to 0 and y is equals to 0. So if I do that, I will have, and also z is equals to 0. Now this is satisfied. X minus y is equals to 0. 0 minus 0 is equals to 0. So I have the vector of form 0, 0, 0, right? So this belongs to x. So this is fine. Now let's do the second part, which is checking for the closed under addition or not. So I'm going to take two vectors. I'll say x1, y1 and z1. These are the two vectors that belong to x2, y2 and z2. They belong to w already. Okay. So another thing that we can derive from here is x is equals to y. Because x minus y is equals to 0, it means x is equals to y. So I'm going to reduce this to the same form. I'll say x1, z1, and I'll say another vector that I'm taking here is x2, x2, z2. You can replace y also, that's not an issue. Now I'm going to add both of them. So I'll add this up. So what am I getting? I'm getting x1 plus x2, x1 plus x2, and I'm getting z1 plus z2. Now let me assume that x1 plus x2 is equals to a and this is equals to b. So the form that I'm getting over here is a and b. Okay. Now from here we took that x is equals to y, right? So I can replace this with c, which is a is equals to c. But this also you can check that this is of the same form as these vectors, right? So hence this is closed under addition because this belongs to x. They are of the same form as these vectors because x is equals to y because x minus y is equals to 0. Correct? So this is closed under scalar. This is closed under addition, right? Now the final thing that we have to check is whether this is closed under scalar multiplication or not. So I'll take it to the next slide. So how will we check whether this is closed under scalar multiplication or not? I'll take a vector which is x, y and z. Okay. And for all c belonging to R, c dot x, y, z should be in x. Okay, so now let's see this. So this is cx, cy and cz. Okay, now I have to check whether cx minus cy is equals to cx minus cy should be equal to 0, right? So here I will take cx minus y is equals to 0 and x minus y is equals to 0 because x minus so this already was there in R in x, right? So it means that they were of the form x minus y is equals to 0, right? So it means this is true. So this is equals to c into 0 into 0 and this is equals to 0. Therefore c of x, y, z is also of the form of these vectors. Therefore this belongs to x. So this is also closed under addition and scalar multiplication. So this third point is also verified. So all these three are verified and hence this is also a valid subspace. So this is also valid subspace. So the correct options in this particular question are A, B and D. So the correct answer is A, B, D. Fine. Okay, now let's do this question. Which of the following is a subspace of R3? Okay, so we have to find which of the following is subspace of R3. So this is an MCQ question. One of them is actually a subspace of R3. So to check the subspace of R3, again we'll do whether there is zero vector, closed under addition. So this is the first thing, this is the second thing, this third thing is scalar multiplication, closed under scalar multiplication. I'm not writing it down, you should understand it now. Okay, so let's check the A option. So we have A 0 0. So when A is equals to 0, it implies that 0 0 0, right, which belongs to this vector space. Let's call this A. So this belongs to A. Therefore this is satisfied. Okay, this condition is satisfied. Now let's talk about the scalar addition, closed under addition. So if I take A1 0 0 to be one vector and I add A2 0 and 0 to it, then I will get A1 plus A2 0 and 0. Okay, if I assume A1 plus A2 is some other value, so let me assume it as B. So the vector form becomes B 0 0, right? So this form belongs to A, right? So this is also verified. Now what about the third part, which is scalar multiplication? So here we'll do this. So we have C into A 0 0. So if I do this, so I'll get CA 0 0 if I can assume CA to be equal to B, so the form that I'll get is B0, 0, and this I know belongs to A. Therefore, this is also fine. This is scalar multiplication. This is closed under scalar multiplication also. So this is option is correct. Now, because this is an MCQ, we can just take this and move forward. But let's, for the sake of completion, let's go through the other options and see why they are not the vector spaces or valid subspaces. So I'll pick this one. So all vectors of the form this. So let me assume, so let me check. So I know what are the three conditions: zero vector, addition, and scalar multiplication, right? So these are the three things that you have to check. Now let me check whether 0, 0, 0 belongs to this. So let me take A equal to 0. So the vector will be of form 0, 1, 1. Correct? But this is not equal to 0, 0 and 0. Right? Therefore, 0 vector does not belong to B. Therefore, not a subspace. Okay. So this is incorrect. Now this is also incorrect because we have found one vector space which is correct. So this is also incorrect. So the only option that we have to check now for our surety is C option. So we'll do that here. So you will again check for these three and see if any of this is matching, because in an MCQ obviously one of these will not get satisfied. So we'll see this. So we have all the vectors of the form A, B, C, where B is equals to A plus C plus 1. Okay. So now B is equals to A plus C plus 1. Now I want to see whether 0 vector exists or not. So to do that, I will try to take the values of A to be 0 and C to be 0. Okay. So I'll take A is equals to 0, C is equals to 0. Now what will be the value of B? If I do this, B will become 1, correct? Because this is 0, 0, 0 plus 0 plus 1 is equals to 1, right? So, and what are the other ways to make the 0 vector? So, apart from doing this, that I take A and C to be 0, there is no other way I can get 0 over there. So, hence, if I do this, then the vector that is coming over here is 0, 0, 1, right? Which is not equal to 0, 0, 0 vector. Therefore, 0 vector not in C, right? Therefore, this is not satisfied. This is here was not satisfied. It's not a subspace. Okay. So hence this option is also incorrect. So the correct option for this question is A. So this is correct. Let's see this question. Which of the following set of vectors are subspaces of R3? Okay, so we have to find out of these 5, which are the subspaces of R3. So let's do them one by one. So I'll take this here. Here I'll take it. Now we know the 3 conditions, right? We have to check 0 vector. Second is addition. The third is scalar multiplication, right? Closed under scalar multiplication. So we'll check with this. So we have all set of vectors. So the vectors are of form x, y and z, where it's saying x, y and z is equals to 0. Okay. So let's check for the 0 vector first. So we'll see if x is equals to 0, y is equals to 0 and z is equals to 0 will belong to this particular, let me call this, say, A option. Okay, so this belongs to A. So I'll get the vector of form 0, 0, 0. So this belongs to A. So this is correct. Now let me check whether this is closed under addition or not. So I'll assume that x1, y1 and z1. I have these 2 vectors, x2, y2, z2. Okay, so another thing to do this simplification is that what you can do is, instead of taking generic examples, right, like I can see here that this does not satisfy. Okay, why I can see it is I have obviously solved many questions on this, so with experience you will get it. But let me tell you one way of doing proofs or solving question is that once you have to prove that it satisfies for everything or every vector in this set, then you have to do these generic proofs. Okay, but if you have to prove that okay, this does not satisfy even for one single vector, an example is enough. So we'll do this with the another approach where we'll take a counter example. Okay, so here let me take a counter example here. So I will take x. So it's saying that x, y, z, if I multiply, this should be equal to 0. X, y, z, multiplication is 0. So let me construct two vectors like that. So I'll take 0, 1, 1. So this is one vector. And then I'll take 1, 0, 1. Okay, this is my second vector. So this is my v1 and this is v2. Now you can check that v1 and v2 belongs to this A set. Okay, so I'll write here v1 and v2 belongs to A, because if I multiply 0 into 1 into 1, I'll get 0. I'll multiply 1 into 0 into 1, I'll get 0, right? So both of them satisfy this condition that x, y, z is equals to 0. Now if I add them up, let me do addition of these. So I'll add 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 2. Right? Now let me multiply x, y, z coordinates of this. So this will be equal to 1 into 2, which is not equal to 0, right? So this I took two of the vectors from this vector space or this set. This is not a vector space yet. So this is a set right now. We are in process of proving whether this is a vector space or a subspace or not. So using the word vector space for this is incorrect. So we should say this set, I took two vectors from this set and I added them up, and this vector, this does not belong to this set A, right? Therefore, this is not closed under addition. Okay. So therefore, not a subspace. So always remember that if you have to prove something that is false, you can take just one counter example and you can say that okay, this is not a valid subspace. Okay, so let's come back to this. So we know that this is not the correct one. Okay, now let's check the second one. So I'll take the second one. Let me call this B. Okay, so 1, 2, 3 conditions: 0 vector, addition, scalar multiplication. So here you have all the vectors of form 3x plus 5y plus z is equals to 0. Now here if I take x is equals to 0, y is equals to 0 and z is equals to 0, this will satisfy this equation 0, 0, 0, right? So this means that 0, 0, 0 actually belongs to B. So this is satisfied. Now let me take the addition part, the closed under addition. So let me take two vectors which are of the form. So let me take this vectors of the form x1, y1, z1. Let this vector and this another vector x2, y2, z2, this let it belong to B. Okay, now I have to prove that the addition should also belong to B. So I will say x1, x2, y1 plus y2 and z1 plus z2. Now how do I prove that this belongs to B? I'll have to check for this condition, whether this satisfies this condition. Now I know that 3x1 plus 5y1 plus z1 is equals to 0. I also know that 3x2 plus 5y2 plus z2 is also equal to 0. Why? Because these two vectors already were there in this set through assumption. I took these vectors from this set, so they have to satisfy these two conditions, right? Now if I can prove that 3x1 plus x2 plus 5y1 plus y2 plus z1 plus z2 is also equal to 0, then I will say that if this equals to 0, then this vector belongs to, then this is closed under addition, right? Because this vector will belong to B, then closed under addition. under addition. Now can you see that this is true? Because if you add these two equations, you will get 3x1 plus x2 plus 5y1 plus y2 and z1 plus z2 is actually equal to 0, right? So this is indeed true. So this is the first equation, this is the second equation. True because 1 plus 2, right? Because of this is true, hence this is closed under addition. Now we have to check for closure under scalar multiplication. So for that we will take this vector which is x, y and z, okay, and I'll take this to be the vector. Now this belongs to B. Now for all C that belongs to C is a scalar that is coming from the real space, I have to prove that C, x, y and z also belong to B. Okay, so let's me multiply this. So I will get Cx, Cy and Cz. Okay, I have to check whether this belongs to B. So what I will do is I know that 3x plus 5y plus z is equals to 0, right? Now let me multiply C to this equation. So I'll get 3x plus 5y plus z is equals to 0. Now I'll multiply C inside. So I'll get 3cx plus 5cy plus cz is equals to 0. Now this I got from this equation, right? The original vector that I had, and I have not done anything wrong. I have just multiplied this with this equation because if this is true, then if I multiply C with this equation, this should also be true. Now this is giving me this form, right? So this actually is of this form. Therefore, this vector Cx, Cy and Cz actually belong to B. So this is closed under scalar multiplication also. Okay, so this is also true. So our option second is actually true. Fine. Now let's see. So another way to reduce your load is check what are the options that will be distinctive in determining whether the option is correct. Right now I'm doing for all the options because I want to show you as many examples I can for finding the valid subspaces or not. But in this question, if you see that second option is actually present in all the options, right? So you could have skipped it because your decision on which option is true, it's not going to be decided by the second option, right? And I know that first is not, so I can eliminate this immediately, right? First I have already checked, so I can eliminate these two. So the only thing that we'll have to check is these two, right? So B and C options we should check. So anyways, we'll do this. Now basis of that, we don't have to check the fourth option also because fourth is not present here. So hence what we'll do is, but we'll check all the options because I want to again show you the maximum examples. But you can eliminate the options if you're careful enough. So let me take the C option. So this is the third option we have over here. We'll again check for zero vector. So you can see that the zero vector is actually present because x, y, z is equals to 0, 0, 0. This will satisfy the equation, right? So this is correct. The second thing is addition. Now I have to check for addition. Now before I jump to addition, observe this. Okay, what is it saying? It's saying x square plus y square plus z square is equals to 0. What does it mean? It means that the sum of squares is equal to 0. If sum of squares is equal to 0, then what does it mean? It means that x square is equals to 0, y square is equals to 0 and z square is also equal to 0, right? That is the only way where sum of squares can add up to 0. Then it means that x is equals to 0 and y is equals to 0 and z is equals to 0. Okay, so the only vector that is present here is actually this vector 0, 0, 0. So this vector space is nothing but a zero vector space, and we know that zero vector space is a valid subspace. So zero vector space. So this is actually zero vector space, which is a valid subspace, valid subspace, right? So we don't have to check for all the options again, but just be observant of these things and you can do these questions quickly. So let's go back. So this is correct. Okay, so third one is there. Now the deciding factor is fifth one. We can skip fourth one, but I will do it, but you can just check the fifth one. If fifth one is there, C is the answer, otherwise B is the answer. So let's do this one. Okay, so we have this x plus y plus z is equals to 1. So we have x, y and z. Okay, let me take x is equals to 0, y is equals to 0 and z is equals to 0. So it means that 0, 0, 0. This vector I want to check whether this belongs to this set, but I'll say that 0 plus 0 plus 0 is actually 0, which is not equal to 1, right? Therefore 0 vector is not there in this set. 0 vector not in the set, therefore it's not a subspace. Okay, so this was easy. This is not. Okay, now we have to check the fifth one. So if you remember the last thing that we did, where x is equals to y, or the equation was given was x minus y is equals to 0. This is same as that. Okay, so this actually we have done before. This is the one here, right? And we saw that this is actually a vector space. So I'm not going to do this again. So this we know from previous question. I'll just write it from previous questions. We have seen this is a valid subspace. Subspace. So if you are confused, please do it again and see for yourself that this is actually true. So this is true. So the correct options are second, third and fifth, which is C option. So your C option is correct. The answer to this question is C option. Okay. Let's see this question. Again, we are asked which of the following is a subspace of P3. Okay. So let's see what is P3 first. So when I say P3, it's basically the polynomials of the form Ax is equals to x0, means x power 0. So this is like x power 0 plus b into x power 1 plus c into x power 3, x power 2 plus d into x power 3. So these are actually the polynomials of up to 3 degree. Okay, so this is nothing but a plus bx plus cx plus d. This is x square, x cube. So these are polynomials of degree 3. Okay, so these are polynomials of degree 3. Now it's asking us which of the options is correct. So here we have to check these two options. So we'll check them. So let me take this first example. Okay. So it's saying all the polynomials of the form a3x cube plus a2x square plus a1x and a0, where a3, a2, a1, a0 are rational numbers. Okay. So what are rational numbers? First of all, rational numbers. So rational numbers are of the form p by q, where q is not equal to 0. So the numbers that you can represent in the form of p by q are rational numbers. So it means that root 2, root 5, root 3, or all these are irrational numbers. Okay. So whenever the rational numbers comes in picture, usually you will see issues with scalar multiplication. Okay, and I'll show you how. So here let me not check for the 0 vector or closed under addition first. Let me check for closed under scalar multiplication. Okay, so because this question does not say anything about the scalars, I am going to assume that C belongs to R. Okay, so in R you have both real numbers. You have real numbers. It means that it can both be rational and they can be irrational also. Fine. So here, because they did not specify where the scalars are coming from, by de facto we will take the scalars come from the real numbers. So suppose I have a vector of this form. I have, say, A3, A2, A1, A0. Okay, this belongs to this vector space A. Let me call this A. Now I am taking C belongs to R. Let me take root 2. Okay, so now I will multiply this root 2 with A3, A2, A1, A0. Now if this is a valid subspace, then this should belong to A, right? But this already said that A1, A3, A2 and A0 are rational numbers. The moment I multiply this irrational numbers to all of these coordinate values, these become irrational. So this will be root 2 A3. This will be root 2 A2. This will be root 2 A2. This is root 2 A1. This is root 2 A0, right? This is a rational number. We already know because this vector is already there in the A subspace or A set. I'm again calling it subspace, but we have still not proved that it's a subspace, so that's not the right way to do it. The correct way to say it, it's a set of vectors. So because this set of vectors already has this A3, A2, A1, A0 vector was already in this set A, it means that A3, A2, A1, A0 are already rational numbers. When you multiply a rational number with an irrational number, you will get an irrational number, right? Now this definitely does not belong to R. Sorry, does not belong to A. A is the subset, right? So therefore this is not closed under multiplication, scalar multiplication. Hence this is not the correct option. Now we have to check whether this is correct or not. This is a valid subspace or not. If this is not, then D will be our correct answer. Otherwise this B will be our correct option. Okay. So let's check for this one. So we have the vector of the form. So let me take this three things. I have to check for zero vector. I have to check for closed under addition, and I have to check for whether this is closed under scalar multiplication or not. So let me check for zero vector first. So I will take A3 is equals to 0, A2 is equals to 0, A1 is equals to 0 and A0 is equals to 0. That will give me 0, 0, 0, 0. And if I add all of them up, so this will also satisfy this particular equation. So hence zero vector is present in this particular set. So my first is done. Now I have to check for scalar. I have to check for addition. So for that what I'll do is I'll assume two vectors. Let me say A3, A2, A1, A0, and I'll say this B3, B2, B1 and B0. I am saying that they both belong to the space B. I'm calling this set B. Okay. So if they belong to B, then it means that A3 plus A2 plus A1 plus A0 is equals to 0, and B3 plus B2 plus B1 plus B0 is equals to 0, right? These conditions are known. Now we have to check whether A3 plus B3, A2 plus B2, A1 plus A2, A1 plus B1 plus A0 plus B0 belongs to B or not. Okay, it will belong if A3 plus B3 plus, I'll sum all of this, A2 plus B2 plus A1 plus B1 plus A0 plus B0 is equals to 0. Then yes, then closed under addition. Can I satisfy this? I can, because of the equations 1 and 2. If I add equation 1 and 2, then I will get this result. So 1 plus 2 is actually true, right? So this also gets satisfied. If I add these two equations, I'll get this equation satisfied. So this is true. Now the only thing that I have to check is closed under scalar multiplication or not. So let me take a vector which is like A3, A2, A1, A0. This already, let this be in B. Now let me multiply. Now I'll write the equation here. A3, A2 plus A1 plus A0 is equals to 0. Because this belongs to, since, let me call this vector B. B belongs to B. Now I have to do C multiplied with this vector A3, A2, A1, A0. For all C belong to R. Okay. So what I'll have to do is I'll have to do C A3, C A2, C A1 and C A0. I will check for this whether this belongs to B or not. So if I add all of this and take C common, A1, A3 plus A2 plus A1 plus A0, I'll get this is equals to, this I know is equals to 0 from this equation, first equation, right? So this is actually equal to 0. So this is 0, right? So this belongs to, because this is of the same form as this that was given over here, that A3, A2, A1, A0 is equals to 0. So therefore this belongs to B. Hence this is closed under scalar multiplication also. So B is actually the correct option. Okay. So B is correct. So the answer to this question is B. Fine. Now let's look at this question. So this question is again asking that which of the following is a subspace of real vector space R3, and we have to select all that apply. So let's again do this. So I'll check. So this is an MSQ question because it's asking which of the following is or are. So you can see that this is an MSQ. So we'll have to check for all the options and see which of them are vector spaces or not. So first of all, I'll check for 0 vector. Okay, how will I check for 0 vector? I will take whether 0, 0, 0 belongs to A or not. So if I take this, I have to satisfy this equation. So I'll put values of x, y and z in this equation and I'll see if satisfied. So I'll say 0 plus 0 square plus 2 into 0 minus 3 into 0 square is equals to 0. This is actually 0 is equals to 0. So this checks out. So this is a 0 vector. A 0 vector belongs to 0 vector belongs to A. So this is correct. Now we have to check whether this is closed under addition or not. So we have to do closed under addition. So how will we do this? So for this, what we'll do is we have to check whether if I add two vectors, it belongs to the space or not. But before this, I want you to observe few things. So here, let's see what is this form meaning. So this is a square and this is also a square. If squares are adding up to 0, it means that they individually are equal to 0. It means that y plus z is equals to 0, which means that z is equals to minus y. And also 2x minus 3y is equals to 0, which means that x is equals to 3y by 2. Okay. So my vectors are actually of the form. So instead of x, I'll write 3y by 2. Then this is y and this is minus y. Okay. So this is the form of my vectors. Now let me assume I have two vectors of this form. So you can simplify this. So I can get rid of 2 over here. I can convert this to 3y. And I'm basically going to multiply it by 2. So I'm getting 3y, 2y and minus 2y. So this is the form of my vectors. Now what I have to do is I will take two vectors. I'll have say 3y1, 2y1 and minus 2y1. And I'll add the other vector which is 3y2, 2y2 and minus 2y2. If I add it, I should get the same form as this. So for this I will do 3 into y1 plus y2, then I'll get 2 into y1 plus y2, and then here I'll get minus 2 into y1 plus y2. Okay, now let me assume y1 plus y2 is equals to say a. So the form that I'm getting over here is 3a, 2a minus 2a, right? So this belongs to a. So this is correct. So this is closed under addition as well. Now let me test it for closed under multiplication. So for this, I'll take this vector which is of the form 3y, 2y and minus 2y. And so this will, I will take c into, c basically comes from some real number. So you have 3y, 2y minus 2y. This is the form of my vector. So here I'll get c into 3y, c into 2y and minus 2y, c into this, right? Now I know that 3y, I know that this form already is satisfied by this vector, right? So hence if I multiply any scalar to this, so this is already satisfied. So this is nothing but saying that x is equals to 3cy and y is equals to anyways 2cy and z is basically minus 2cy, and if I add them up, say I'm going to do this form, this should give me 0. This is the form that I have. So I'll add y plus z. So y plus z is equals to my 2cy minus 2cy, which is equals to 0. So this became 0. Now I have to do 2 times x, which is 3cy minus 3 times y is 2cy. So this is nothing but 6cy minus 6cy, which is equals to 0. So this also became 0, right? So this equation is being satisfied with this vector. Therefore, this belongs to A, right? So this is closed under scalar multiplication as well. So I'll write here closed under scalar multiplication. Fine, so the option is actually correct. This is correct. Now let's take the second option. This is our second option. Now here, like you can, so what is this? So this is x, y and z, okay? And y belongs to q. What is q? Q is again the set of rational numbers. So if you don't know this notation, you should know that this is rational numbers. So like I told you in the previous questions, whenever this kind of restrictions come, right, the usual issue is with the scalar multiplication. The set might not be closed under the scalar multiplication. So we should check for that first. So let me assume that this is a vector. Okay, so let me say this, that I have a vector like this 0 0 0 0 1, right? Now this I'm saying belongs to B. B is the option. I'm saying this is the same set. Now I'm saying I'm going to multiply it with root 2. So I'll say 0 root 2 into this vector. Okay, so I will get 0 root 2 and 0. Now this does not belongs to B because this is irrational, right? But you told in the description itself that y should be a rational number. So this is not closed under scalar multiplication. So whenever you see this conditions of rational, start with the closure under scalar multiplication. That will be a better choice. I'm not saying always it will be the issue that this will not satisfy, but usually you will see that issue happen whenever they try to restrict it to the rational numbers. Now let's see this third option, which is this one. So here let's have this C option. Now let's see what is the issue here. So we have to check first for zero vector, then second for addition, and third for scalar multiplication. Okay, now I am seeing, so let me check with 0, 0, 0 first. So this should belong to the C option, and it does because y into z. So this is y, this is z. Both in if I do multiplication, that will come out to be 0. So this checks out. Now I'm saying that I have two vectors. So let me take two vectors like this. So I'll check the closure under addition, and usually these multiplication kind of things, right, they'll give you an issue whenever you're checking for closure under addition. So let me say that I have a vector like this, 1, 0, minus 1, and I have here, so here y into z is equals to 0. Here let me say this is the vector, I'll say minus 1, and this is 0. Okay, these are my two vectors. You can check that they actually belong to C. Now I'll add them up. So I'll do 1 plus 1 is 2. Now 0 minus 1 is minus 1, and minus 1 0 is minus 1. Okay, now this does not belong to C, since minus 1 into minus 1 is not equal to 0, right? Therefore this is not closed under addition. So I took two vectors from this set of vectors, and I took the counter example. I looked at this and I could see that, okay, this is, I can take a counter example over here. So I took a counter example, and I am showing that I took those two vectors from this set C. They satisfied this form where y into z is equals to 0. But when I add them up, I don't get a vector such that y into z is equals to 0. Hence, this is not closed under addition. Okay, hence therefore it's not a subspace. So this option is also incorrect. Now we have to check this option. So we'll check the zero vector, addition, and scalar multiplication. Okay, 1, 2, and 3. Fine. So we have to find vectors such that they satisfy this form. So first of all, I'll check whether 0, 0, 0 belongs to this vector D or this subset D or not. So I'll try to put this. So I'll have 2, 0 plus 2, 0 minus 3, 0 plus 1 should be equal to 0. But when I add this up, I will get 1 not equal to 0. Okay. So this itself is not satisfying. So 0, 0, 0, the vector does not belong to D. Therefore, not a subspace. So only one option is correct. Okay. So this is also incorrect. So only A option is correct. So the answer to this question is A. Okay. Now let's solve one more question. So this question was asked on our Telegram group. I don't know where this question is from, but this was asked on our Telegram group by some student. So let's see this. So this is a slight variation of the vector spaces and subspaces. So here it's saying that consider the vector space V, that is R2. We define vector addition in this vector space as this. So now here in the previous questions, what we have seen is that the multiplication and the addition of the vectors was being inherited from the original vector space, right? But here they are changing this definition. They're now describing a new way to add vectors and a new way to multiply scalars to the vectors. So the vector addition is defined like this, and the scalar multiplication is defined like this. Then the zero vector in this vector space is. So this is here what it's asking is that what is a zero vector in this vector space. So first of all, let's understand what is the meaning of zero vector in terms of vector space. So zero vector in usual sense means that if I take any vector that belongs to the vector space, and if I add the zero vector to this, I should get back V1. Okay. Now because here the vector addition has been defined very differently, you will not get, if you add like a 0 0 0 vector to this or 0 0 vector to this, you will not get the same vector back. So here let's say that this I'll copy, and here let's see this. Okay, let's say I will add u1 u2. Let's say this is a vector that belongs to this new defined subspace, and here I add the 0 0 vector. Okay, I'm going to add the 0 0 vector using the vector addition that has been described in the question. So this is nothing equal to, this will be u1 plus 0 plus 1, and this will be u2 plus 0 plus not plus, minus 2. Okay, now this is going to be equal to u1 plus 1, and this is u2 minus 2. Okay, so this is not giving me the vector, so this is not equal to u1 u2, right? So hence this is not the 0 vector, not 0 vector. This is not 0 vector of this space, of this subspace. So in this subspace, because we redefined the way we add and multiply the scalars, the definition or the vector that is going to be the 0 vector in this has changed. Fine. So we have to find that 0 vector. So the vector, so we'll use the same property over here to find that vector. So let's assume t1 t2 is the 0 vector here. Okay, so t1 t2 is a 0 vector. So if I take any vector here, say u1 u2, and I add the 0 vector here, t1 t2, then I should get back the same vector u1 u2. Okay, this is by definition of 0 vector. If you have not seen this, you can watch the lectures on vector spaces that I have added before in this playlist, so that you understand how the 0 vector works. And this comes from one of the axioms of the vector spaces. Fine. So this is by definition. Now I'm going to use the redefined version of addition over here to solve this. So here, let me copy this. How do I add these two vectors? So I'm saying that u1, I am going to add these two using this vector space, using this vector addition. So this is nothing but u1 plus t1 plus 1, and this is u1, this is actually u2 plus t2 minus 2, and I'm saying that this is actually equal to u1 u2. Okay, if this has to be equal to u1 u2, then this means that t1 plus 1 should be equal to 0, which gives me t1 is equals to minus 1, and here t2 is equals to t2 minus 2 should be equal to 0. Then only we will get the u1 u2 vector back, right? So here t2 is equals to 2. Therefore the 0 vector in this subspace is minus 1 2. So this is how you solve this question. So the answer of this question is minus 1 2. Fine. Okay, now let's move on to another question. So this was also asked on our Discord group. So if you have not joined our Discord group, you're part of test series or your full course enrolled, please check your emails and you can join the Discord group. Let's see how to solve this particular question. So we'll take one option. So again, it's saying which of the options are correct. So they are saying this is a subspace, this is a subspace, this is a subspace, this is a subspace. Okay, so we'll take them one by one and try to solve them. So we'll take this here. This is my A option. So here I have to check whether this is a subspace of R2 or not. So I'll check whether 0 0 belongs to this A. Okay, so all the vectors are from 1A. Okay, so I have 1A. Right, so it means that on the first coordinate I can never get a 0. First coordinate means this one, this. this is first coordinate. Okay, so the first coordinate can never be 0. Therefore 0 0 vector does not belongs to A, therefore not a subspace. So this is incorrect. So this we got that this is incorrect. Let's check the B option. Here is the B option. So we have vectors of the form S and T minus 1. Okay. Now let me set S is equals to 0 and T is equals to 1. Okay. If I do this, I'll get a vector of form 0 0, right? S is equals to 0 and 1 minus 1 is 0. So for some value of S and T, this belongs to B, right? 0 0 vector, 0 0 vector belongs to B, right? So therefore the first condition of 0 vector is satisfied. Fine. Now let's check the second portion, which is the closure under addition. So here I'll assume that I have two vectors S1, T1 minus 1, and I also have S2 and T2 minus 1. Let me add them up and see. So I'll get S1 plus S2. I'll have T1 plus T2 minus 1 minus 1. Okay. Now this is S1 plus S2, T1 plus T2 minus 2. Now this is a point where a lot of students can make a mistake. They can say that, oh, this is not of the form ST minus 1, hence this is not a valid subspace. But that's not correct. Okay. So you have to check that this form should be made, that ST minus 1, where S and T are from the real numbers. Okay. So here let me rewrite this as, say, K. Okay. And let me write it as J minus 1, where I'm saying K is equals to S1 plus S2 and J is equals to T1 plus T2 minus 1. Okay. So here S1 plus S2, I only have to check whether S is a real number. So this is real number. This is a real number because S1 plus S2 and S1 was a real number, S2 was a real number. So K is a real number. K is a real number. Similarly here we have to check whether J is a real number. So T1 was a real number, T2 was a real number, minus 1 is a real number. So J is also a real number. So I am able to reduce it to a form J minus 1, where it's taking this form where K and J are real numbers. Hence this is also closed under vector addition. Fine. So very important point, a lot of students can miss out on this, and I'm again stressing on that you should not give up here, oh, this is T1 plus T2 minus 2. You should look at the condition on S and T. S and T should come from the real number. That's the condition, right? So therefore, you have to reduce this to a form and you have to check whether that reduced form contains the real number or not. Here, K and J, once I reduce this is actually a real number and hence this is correct. Okay, so this is closed under addition. Now I am going to check whether this is closed under multiplication or not. So I'll take this vector T minus 1. Now if I multiply C, any C from the real number line, and I'll, what will I get? I'll get C into S and C into T minus C. Now again see this is real because real number into real number is a real number. Again real number into real number is a real number, minus real number is a real number, right? So this is also real, right? So this also belongs to your option B or set B, right? Therefore, this is closed under scalar multiplication. Fine. So this B is actually a valid vector subspace. Fine. Now let's see the C option. So let's see this. We have x square and x square and x belongs to R. Okay. Now here x square is there. Okay. So every value in this subspace is of the form this. So for example, 1 1, okay, you'll have 4 4, or you will have 9 9, okay, and many more. Now this is very easy to disapprove using an example. Let me take these two, let me add them up. 1 1 plus 4 4, okay, and I'll get 5 5. Now this 5 5 is actually not of the form x square, right? 5 is not equal to x square. Right? It's not a square of some number. Therefore, this is not closed under addition. And how did we prove this? By using a counter example. So when you have to disapprove something, you can always use a counter example, that is sufficient. So this is not the correct subspace. This is not a subspace of R2. Now let's see the final one, which is this D. Now you have x, 2x, x, 2x plus y. Now let me take x, y, z of this and let me take them to be 0, 0, 0. Okay, I want to check whether 0, 0, 0 belongs to this set D or not. So if this is the case, then we have to put these values over here and see. So if x is equals to 0, x is equals to 0 and y is equals to 0, what do we get? We'll get 0. 2 into 0 is 0 and 2 into 0 plus 0 is 0, right? So for x is equals to 0, y is equals to 0, this belongs to D, right? So this is 0 vector is there in this. So first condition is satisfied. Now we have to check for the second condition, which is addition, which is closure under addition. So I'll take two vectors. I'll take x1, 2x1 and 2x1 plus y. I'll add these. I'll take these two vectors which belong to this set D. So I have these two vectors which are already belonging to this set D. Okay, and I have to add them up. Let me add this up. So they belong to D. So I have to see whether the sum also belongs to D. x1 plus x2, 2x1 plus 2x2, and I have 2x1 plus y1 plus 2x2 plus y2, right? Now I can say rearrange these a bit. x1 plus x2, 2 into x1 plus x2, and then I'll have 2 into x1 plus x2 plus y1 plus y2. Okay, now this is of the same form as this, therefore this belongs to D, and hence vector addition is closed here. Now we have to finally check for scalar multiplication. So how will we check for scalar multiplication? I'll take a vector which is 2x, sorry, this is x, 2x, 2x plus y, and let me multiply it by c, where c belongs to R. So I'll get cx, c into 2x and c into 2x plus y. Now I'll have it as c into x, 2 into cx, 2 into c of x plus cy, right? Let me replace cx is equals to a and cy is equals to b. So the vector form that I'll get is a, 2a, 2a plus b, right, which belongs to D. Therefore this also, third condition is also satisfied, scalar multiplication. So this is a valid subspace because all the three conditions are satisfied. Okay, so the answer to this question is, the correct statements in this are A and D. Sorry, B and D. Yeah, the correct answer is B and D. So The answer is B and D. B and D are the correct subspaces. Let's see this question. This is from our test series. So I was surprised actually to see how many students have marked this incorrectly. So this is from our test series. So let's look at this. So given that S and T are subspaces of vector space, which of the following is or are not always a subspace? So this is a MSQ kind of question, and they have said that S and T are actually subspaces of some vector space, and which of the following is not always true. Okay, so you have to tell that which is not always a subspace. Fine. So first of all, select all that apply. So we have to find the options which are not going to be a subspace always. Okay, so let's start with option A. So option A is S intersection T. Okay, so this actually is always a subspace. So this is always a subspace. You can actually very easily prove this, that a vector that belongs to X, let's say X belongs to S and X belongs to T. Okay, then definitely this will belong to the intersection, right? Now all the linear multiples of X will belong to the intersection, and the zero vector, because it belongs in S and T both, it will also belong in the intersection. Okay, so so this is vector Cx belongs to S and Cx belongs to T, then X will belong to S intersection T, and zero vector belongs to S, zero vector belongs to T, then 0 will always belongs to S intersection T. Okay, so this is always a subspace. So this is always a subspace. I'm not doing a very rigorous proof in this, but just know that this is always a subspace. Okay, fine. So this is not our answer. Let's see S union T. So what is the meaning of S union T? Okay, so it means that S is a set of vectors which forms a subspace, right? This is also a set of vectors, and if I take a union of these two sets, I'm saying that that has to be a subspace. Let's check that. So I'm going to give you a very visual representation of this. Suppose that you have a subspace like this. You have this two-dimensional, this R2 is there, and you have two subspaces. Let me see that this is the first subspace. So let's say that this is your first subspace over here, and let's say this is S and this is T. Okay, now what is the meaning of S union T? S union T means all the vectors which are on this line and all the vectors which are on this line. So let me take an example. Maybe say here this is, say this is 1, this particular vector over here. Let me take this vector over here. Say this is 1, this is 2, and this is 1. Let me take this vector 1 2, sorry 2 1. Now this 2 1 belongs to T. Okay, and let me take another vector which is on this. Let me take, say, 2 1. This is 1 2. Now I have 1 2 which belongs to S. Okay, so if S and T are subspaces, so you can clearly see that there are subspaces here. H is a subspace of dimension 1 and T is also a subspace of dimension 1, right? Then x1 that belongs to S and x2 that belongs to T. the S union T, right? So x1 plus x2 should also belong to S union T. Okay, because x1 belongs to S and x2 belongs to T, or you can say that it belongs to S union T or T union S, and hence their addition should belong. Now what is the addition of this? So if I add this up, I'll get a vector 3 3. Okay, 2 1 plus 1 2, right? So that is equal to 3 3. Now where is 3 3? So this is 3, this is 3. So this vector is going to be somewhere here, right? Now this vector, this is the vector 3 3. This does not belong to S union T, right? So all the vectors that are on this S, on this line, are in S. All the vectors that are on this line T are in T. But their addition, I have taken just one counter example. I am adding them up and they are not in T, right? So this does not belong to T. So therefore, by counter example, I have shown you that this is not always true, that S union T is a subspace. Okay, so this is not always a subspace. When will this be a subspace? This will be a subspace when one of them is a superset of the other set. Okay, so this is right now correct. Now let's say 2s. So what is the meaning of 2s? So 2s, right? So what is happening in S? So S had vectors v1, v2, v3 up 10. Some vectors were there, right? What is 2s? 2s is nothing but you have multiplied every vector that this vector space S had. You have just multiplied them with 2. Okay, so you have just taken like multiples of 2. So for example, suppose you had a vector space, this is R2, and in this you had this line as your space S. Okay, so what you have done is you have taken just, so if this was a vector, say 1 1 was a vector, this is 1 1. Okay, this is 1 1. Now what will happen is in this new space S dash, that will be 2 2. That vector will become 2 2. Okay, so by seeing this you can argue that this will be a valid subspace because it's just a linear combination of the existing subspace. But let's prove that. So we'll take with 0 vector space, 0 vector, whether we have 0 vector in this or not. So we know that 0 vector was there in S, right? So now 2 into 0 vector will be equal to the 2 times, we are basically multiplying every vector by 2, right? So therefore 2 0 will belong to 2s, correct? Because we are just multiplying the 0 vector by 2, so it means 0 vector belongs to 2s, correct? So 0 vector is fine. Now what about the addition? Is this closed under addition? So I know two vectors u1 and u2, they belong to S, right? Now 2u1 and 2u2 will belong to 2s. Now I know u1 plus u2 belong to S. Then I have to check whether 2 times u1 plus 2 times u2 belong to S, 2s. I have to check this. So how will I check this? So I know that since u1, u2 belong to S, then it means u1 plus u2 belong to S, right? Then it means, right, so u1 plus u2 already belong to S. So when I take 2s, it means 2 times u1 plus u2. So this vector u1, u2 which was there in S became 2 u1 plus u2 in 2s, right? So this belongs to 2s. This is nothing but 2 u1 plus 2 u2 belongs to 2s, right? Therefore closed under addition. Now we have to check whether this is closed under scalar multiplication. So we already know that this S is a subspace, right? So 2s is nothing but a scalar multiplication. You are multiplying every vector with 2, right? Hence this is by default closed under scalar multiplication, because you have just multiplied every vector by 2, right? So multiplying every vector by 2, it means that you're just doubling the vector, and we already know that the linear combination of every vector is present in the set 2s, and we have seen that the multiples of the vectors are also present in the set S and 2s. In the set S, so 2 times the vectors will also be present in the set, right? Hence with this argument you can say that this is also closed under multiplication. So this will always be a subspace. So this is going to be a subspace always. Fine. So this is not our answer, because we are supposed to choose the sets which are not a subspace always. Now let's check this D option now. So this is our D option. So what is the meaning of this option? First of all, this is saying S plus T, where S plus T is defined as S plus T, S belongs to S and T belongs to T. Okay. So if I have to talk in terms of the vectors, or let me show you an example over here. What is the meaning of this? So suppose this is your, suppose this is my R2. So this is my R2. Okay, this is R2 and I have a vector subspace which is here. Let me again use the line only. So this is one vector space. Then say this is another vector space. So here this is say S and this is say T. Okay. So what is the meaning of S plus T? Suppose this is a vector that is coming from here. Okay. And this is a vector that is coming from here. Then your vector in S plus T is going to be sum of that. So every vector I'll take from here and I'll add it with all the vectors that are present on S. Similarly, all the vectors I'll take from here and add them to all the vectors that are present there. And I'll, whatever total set I have, that I'm calling as S plus T. Okay. So let's see for 0 vector first. So 0 vector will be present because 0 vector plus 0 vector, 0 vector plus 0 vector gives me 0 vector. So this is present in, because 0 vector is present in S, 0 vector is present in T, so it will belong to S plus T. Now closed under addition, by the definition of this is closed under addition, right? Because say X belongs to T, S, and Y belongs to T, then X plus Y is going to belong to S plus T by definition, right? So this is also closed under addition. Fine. Or you can say X belongs to S plus T, Y belongs to S plus T. Okay. Then I have to check whether X plus Y belongs to S plus T. So here you will make cases that it can be that X and Y belong to S. If that is there, then X plus Y belongs to S, and because it's an S, it will be in S plus T. S plus T how? We'll just add 0 vector to that. Fine. The other case could be ki X and Y belong to T. Then also X plus Y will belong to T, and I'll just add a 0 vector and that vector will belong. The third case is X belongs to S and Y belongs to T. Then X plus Y belongs to S plus T. This is by definition. Right? So this is also closed under addition. What about the multiplication? The scalar multiplication. So I want to check whether X, if X belongs to S plus T, then does Cx belongs to S plus T? So say x belongs to S, right? Then therefore x will belongs to S plus t, because Cx will belongs to x plus t, because Cx already belongs to t, belongs to S, and Cx plus 0 will belong to S plus t. Same argument you can do over here with t. Suppose that x belongs to t and it's not coming from your S subspace. So therefore Cx will belongs to S plus t. Why? Since Cx belongs to t, because t was a valid subspace, then I can just add Cx plus 0. 0 already belongs to S plus t, and therefore this belongs to S plus t. Okay, so this is the case. So in both the cases your vector will exist. Fine. Or it can be that x belongs to S plus t only. Fine. It's not coming from S, it's not coming from t, it's actually a vector that is coming from the addition of that. Then C of x is nothing but C of x1 plus x2, where x1 comes from S and this one comes from t. So what I'm saying is that x is actually a vector that came after I added a vector from S and I added a vector from t. They were not individually present in S and t. Okay, so this is important. Focus here, this particular part. Then I'm saying that Cx should belong to S plus t. So for that, what I'll do is I'll break down this x. X is coming from two vectors, which one was present in S and one was present in t. Now this is nothing but Cx1 plus Cx2. Now Cx1 is present in S and this is present in t. Why? Because S and t were closed under multiplication, right? So this was present. So if they are present in S and t individually, that implies that they'll be present in S plus t. Fine. Hence this is also closed under multiplication, and hence it's a valid vector subspace. So this is also always a subspace. Fine. So actually this is not the option that we are going to tick. So this is always a subspace. So this is asking that which of this is not always a subspace. Hence D is always a subspace. So this is not the right answer. So the answer to this MSQ question is just option B. So B is the correct answer. Fine. Now let's look at the next question. Which of the following set of vectors alpha of the form alpha 1 to alpha n in Rn are subspaces of Rn, where n is greater than or equal to 3. Okay. So it's talking about subspaces R3, R4 up to Rn. We don't know what's the value of n. We know that this is greater than n. This is greater than or equal to 3. Now we have to check for all these options, and we have to, so this is another MSQ question, and you have to find all of them which are valid subspaces. Fine. So we'll look at them one by one. So let me start with the first option. That is option A. So this is option A. So we have the vectors like this. So let's say this is alpha 1, alpha 2 up to alpha n. So this is my vector. And if you are more used to seeing the vectors like this, you can write it as alpha 1 up to alpha n. Okay. Now it's saying that all such alphas, so this is one vector, all such alphas such that alpha 1 is greater than or equal to 0. So can I see that 0, 0, 0 belongs to this set? It does, right? Because alpha 1 is equals to 0 and alpha 1 should be greater than or equal to 0, right? So therefore 0 vector is in subspace. Now I can see things, so I'm going to use a counter example. Let me say that I have a vector like this. I have 1, 2, 3, 4. Okay, this is a valid vector. I'm saying that okay, my n is equals to 4. Now they have not told me anything about the scalars, so I'm going to assume that scalar comes from R, right? So I'm going to choose c is equals to -2, right? So I'm going to see whether c into this exists in the space or not. So this is going to be -2, so I'm going to multiply it with -2. So this is -2, this is -4, this is -6, this is -8. Now this does not belong to A. Why? Because alpha 1, which is this, is alpha 1, right? Now here alpha 1 is actually not greater than equal to 0. So this condition got violated, right? So therefore this is not closed under scalar multiplication. Okay, hence this is not a valid subspace. Now let's check the option 2. Okay, so I have all the alpha vectors such that alpha 1 plus 3 alpha 2 is equals to alpha 3. So suppose you have alpha 1 here, alpha 3 here, or let me say alpha 2 here, then here you have alpha 1 plus 3 alpha 2. Okay, so first of all let's check whether 0 vector is there or not. So if I take alpha 1 is equals to 0 and alpha 2 is equals to 0, then I will get a 0 vector, 0 0 0, right? Because alpha 1 is equals to 0, alpha 2 is equals to 0, alpha 1 plus 3 alpha 2 will be equal to 0, so this belongs to B. So 0 vector is present. Now I have to check whether this is closed under multiplication, closed under addition. Okay, so I will take two vectors. I'll say alpha 1, alpha 2, alpha 1 plus 3 alpha 2, and I'm going to use beta, but it will be of the same form. Okay, so beta 1, beta 2, this is beta 2, and I'm saying beta 1 plus 3 beta 2. I will add it and I'll get alpha 1 plus beta 2, alpha 2 plus beta 2, and alpha 1 plus beta 1. So I'm simplifying this in the steps because I've done it multiple times, but you break it down and then try to rearrange it, but you will get this form, alpha 1 plus beta 2. Now if I take alpha 1 plus beta 2, sorry, alpha 1 plus beta 1, this is beta 1, this is beta 2, this is alpha 1, this is alpha 2 plus beta 2, right? So I'll take alpha 1 plus beta 1 is equals to A, and I'll take alpha 2 plus beta 2 is equals to B. Now if you put these values, we will get the same form of the vectors from here, right? So hence this is closed under addition also. Now we have to check whether this is closed under scalar multiplication. So here we have the vector of form alpha 1, alpha 2, alpha 1 plus 3 alpha 2. Okay, let me multiply it with C. So I'll get C alpha 1, C alpha 2, and I'll get C alpha 1 plus C 3C alpha 2. So let me say C alpha 1 is equals to say A, and I'll say C alpha 2 is equals to B. So I'll get the vector of the form A, B, A plus 3B, right? So therefore closed under addition also, sorry, closed under multiplication also, scalar multiplication. So hence this is also correct. So this is correct. So this is a valid set. Now let's check this C option. So here you have alpha square, alpha 2 square is equals to alpha 1 square. So here you have say alpha 3, here alpha 2 is equals to alpha 1 square, and here you have alpha 1. Okay, now this is very easy to see that this will not hold under the addition. Okay, so let me assume that this is one vector and this is beta 1 square, and you have beta 3. Okay, let me add that up. So I'll have alpha 1 plus beta 1. This is alpha 1 square plus beta 1 square, and this is alpha 3 plus beta 3. Now this second one, so this is, let's say alpha 1 plus beta 1 is equals to A. Okay, now here if this is A, then this should have been A square, right? But so I'll highlight this in this. Alpha 1 square plus beta 1 square is not equal to alpha 1 plus beta 1 square whole square, right? Therefore this is not closed under addition, vector addition. Okay, hence this is not a valid subspace. This is not a valid subspace. Now let's see look at the C option, which is alpha 2 is rational. Now again, something they have given about rational, right? And they are telling us to do the scalar multiplication with real numbers. So this is clear that this is not going to be closed under scalar multiplication. So I'll take a vector where I have alpha 1, alpha 2. So I'll take this vector, say 1, 2 and 3, right? So this belongs to D, since alpha 2 is rational, right? Alpha 2 is this second coordinate. So now I'm going to do root 2 into this vector 1, 2, 3. This is going to give me 1. This is going to give me root 2, 2 root 2 and 3 root 2, right? Now alpha 2 is irrational, right? Here alpha 2 is not rational. Therefore not closed under scalar multiplication. So hence this is also not a valid subspace. So the only answer to this question is B. So B is the only subspace which is valid. The other sets are not valid subspaces. Now let's see this particular question. So it's asking which of the following is a vector space. So here are 4 options. So we'll see each of them one by one. So the first option is this one. So I'll copy this here. So we have the set of all vectors of real numbers are of the form x 0 0 0 with standard operations in R4. So first of all we should check whether the 0 vector is in there. So 0 vector is indeed there, because if I take x is equals to 0, the vector will be of form 0 0 0 0, right? So this is actually true. Now we have to check for additive closure. So how will we check additive closure? We'll take 2 vectors, x1 0 0 0 and x2 0 0 0. If I add them up, then I'll get x1 plus x2 and all will be 0. All the other coordinates will be 0. So this belongs to the vector subset, right? So this is also true. Now I have to check for multiplicative closure. So it means that C that belongs to R, then Cx should also belongs to A if x belongs to A. So let me multiply this with this. So it is giving me Cx and 0 0 0. This also belongs to A because this is of this form. Hence this is a valid vector space. Now what is this vector space really? So in R4 this is actually the x axis, right? Because only the x values are changing and rest y, z and maybe w is constant or is 0, right? So this is the x axis we are talking about, and we know that this is x axis, so it has to be a vector space. So this is true. Now let's check the second option. Set of all pairs of real numbers of the form xy where x is greater than or equal to 0 with standard operations in R2, right? So we have seen this example before, right? So in this case, I can take a counter example and prove that this is not correct, right? Because suppose I have a vector, say 1, 2. This belongs to B set, right? Now I take C to be equal to -1 and I say that I am multiplying -1 with 1, 2, this vector. So I will get -1 and -2. Now this does not belong to B, right? Therefore, this is not closed under scalar multiplication. Fine. So hence this is not correct. Now let's check the C option. Now in this option, what we have is that the scalar multiplication has been redefined. So suppose that k is the scalar and you are multiplying it with the vector xy. So the way you are now multiplying is you are doing k square x and k square y. Okay. Now this is easy to see. Okay. So let's see this combination. So suppose I am doing k1 xy plus k2 xy. Okay. So here this is nothing but I am doing k1 plus k2 into xy, right? This is multiplication, right? Now I will do both of these sides and they should be equal. If they are not equal, hence means this is not this scalar multiplication is not defined well for a vector space. So let me do this part over here. This will be here. So this is k1 xy plus k2 xy. So this is equal to nothing but k1 square x and k2 square y plus, sorry, this is k1 only. This is k2 square x and this is k2 square y. Okay. Now if I add them up, I will have k1 square plus k2 square x. Right, this is getting multiplied with this, or let me write it like this, x. This is my first coordinate and the second coordinate is k1 square plus k2 square into y. Okay. Now let me do the other part. So this basically is saying that we have to do k1 plus k2 square x and k1 plus k2 square y, right? Now these two are actually not equal, right? So the multiplication is not defined well. Both of them are not coming equal. Hence this is not defined correctly. Hence this is not a correct vector space. So only A is correct. So the answer to this question is A. Okay, so A is correct. Now let's look at this question. Here we have been given two subspaces V1 and V2 which are 4-dimensional, and there are subspaces of a 6-dimensional vector space. Fine. Then we have to find the smallest possible dimension of V1 and V1 intersection V2. Okay, so for these kind of questions, first of all, we should know that there is something called as dimension equation. So that is nothing but it says that the dimension of V1 plus V2, okay, is equals to dimension of V1 plus dimension of V2 minus dimension of V1 intersection V2. Fine. So what essentially it's saying is that suppose you are in R2, okay, and you have two vector spaces. Say this is one vector space, this is say S1, and this is your another vector space which is passing through origin, this is S2. Then it's saying that the vector spaces, if they are just disjoint, like these are, right? So in the dimension, so the intersection of these two vector spaces is nothing but a 0 vector, right? So the dimension of that 0 space is 0. So the dimension of this vector space and this vector space actually adds up to the dimension of whole R2. Okay, now if we talk about say R3, then in R3 the dimension of a 2D plane and dimension of a line will actually add up the whole R3, right? And so on and so forth. So this particular formula you can use. So let's look at this, how to solve this particular question. So we have been given that dimension of V1 is equal to 4 and dimension of V2 is also equal to 4. Okay, and the maximum dimension they can have is actually 6. Why 6? Because they both the maximum dimension by adding these two vector spaces can be 6 only, because they can't span more than a 6-dimensional space, because there are subspace of 6-dimensional space. So it means that the dimension of V1 plus V2 is actually less than equal to 6. Fine. Now the dimension of V1, so it's asking what is the smallest possible dimension of V1 plus V2. So let's look at this equation. This is dimension of V1 plus V2 is equals to dimension of V1 plus dimension of the V2 and minus the dimension of V1 intersection V2. So we know that the maximum dimension over here for V1 plus V2 is actually 6. Okay, so here we know that this dimension cannot exceed 6. So 6 should be equal to the dimension of V1 we know plus dimension of V1 we know. So what is the maximum dimension of V1 plus V2? That is 6, because they are subspaces of 6-dimensional subspace. So they can't exceed 6. And when we take the maximum here, then we'll get the minimum intersection over here. So this is dimension of V1 intersection V2. So this is nothing but 8, and you will basically reorganize this. So you will have dimension of V1 intersection V2 is equals to 8 minus 6 is equals to 2. Okay, so how is it the minimum dimension? Because I have considered the maximum dimension that it can take up. So the dimension of V1 plus V2 can range from 4 to 6, right? So the dimension, if dimension is 4, if suppose the dimension of V1 plus V2 is total 4, then the dimension of V1 intersection V2 will be equal to 4, right? So let's say this is V1 plus V2 dimension. Here I am writing V1 intersection V2 dimension. So here B dimension will be 4. Now suppose if V1 and V2 combined together, they span a whole space of 5 dimension. Then your V1 V2 intersection will have the dimension of 3. And when they span the whole R6 or the 6-dimensional space that they are subspace of, then the dimension will be 2. Hence the minimum dimension that V1 intersection V2 can take is 2. So the answer to this question is 2. Okay, fine. Now let's see this question. Consider the set of column vectors defined by x, where x is coming from R3, such that x1 plus x2 plus x3 is equals to 0 and x transpose is written as this. Which of the following is true? So we have to find which of the following statement is true. So this is a MCQ question. Let's see the first statement. So the first statement says that 1 minus 1 0 transpose and 1 0 minus 1 transpose is the basis of subspace of x. Okay, so let's see what is the subspace x that we have. So this is x1 plus x2 plus x3 is equals to 0, right? Then I can write x1 plus x2 is equals to minus x3, or you can write it reverse, that x3 is actually equal to minus x1 plus x2. Okay, so my vector will be of form x1, x2, and this will be minus x1 plus x2. Okay, so this is how my vectors in this set look like. Now let's take the first option and see. It's saying that this is a basis for this particular subspace X. Okay, first of all, we should confirm that this is a subspace or not, if it's not already given. So they are just defining it as a set. We don't know whether this is a subspace or not. So for that, we'll check whether the 0 vector is present or not. If I take x1, x2 to be 0, then 0 vector is there, right? 0 is there. 0 vector is there. Then check whether the addition it's closed under addition or not. So it is actually closed under addition, and it is also closed under scalar multiplication. Okay, so you can do these checks now yourself because we have done so many questions on them, so this should be doable now. So this is actually a subspace. Fine. Now it's saying that two of these vectors is the basis for this subspace. Now how do I know that there are only two vectors that have to be there in this subspace? Okay, so see this. Here you have x1 and x2, right? So this is itself the hint that here you will need two vectors because there are two different values that you will have to pick. So one vector will be of the form, say 1, 0 and minus 1, right? So this is on one vector space. The other is if you are going to find the vectors, the basis of this, so maybe this will also form the basis of that. This is one of the bases, right? Now if this is the basis of that, so what we understand is that I need two vectors in my basis, two linearly independent vectors in my basis to form the basis for this subspace. So this is a two-dimensional subspace. So this is a 2D subspace. Okay, so if I have to check whether this is a basis of subspace X or not, all I have to do is I have to check whether this vector is of the form of this or not, and this vector is of the form of this or not. And if they are, then I have to check whether they are linearly independent or not. So the first thing that you have to check is whether these two vectors are of this form. Let's check. So 1 minus 1. So you have to add all of these three coordinate values, 1 minus 1 0. So this is equals to 0. And this is also equal to 0. So they are actually of this form. Now you have to check whether they are linearly independent or not. So by the look of it, you can actually check whether they are linearly independent or not. So this is 1 minus 1 0. And this is 1 0 minus 1. Another way to do it is you can put them in the matrix and you can find the number of pivots you have. So you will find that there are two pivots in this. So this is actually, these two are linearly independent. So because they are linearly independent and the subspace is of two dimension, hence so this is linearly independent, and also there are two vectors in this. So this is actually the basis for this subspace. So this option A is actually correct. Now option B is that this is a linearly independent set, but this does not span X. Therefore, this is not a basis for X. Okay. So I have seen, so this is actually from our quiz and I saw that a lot of students actually take this because when they tried to find the basis for this particular vector based on these vectors, they were able to find this and they thought that this is not matching the basis that has been given in this. So this is not the correct basis, but they forgot the fact that any two linearly independent vectors from that particular set will actually form the basis, right? So if these two vectors are linearly independent and they are satisfying this condition that has been set for this particular set of vectors, then they will actually form the basis. So because A is true, B is false. Then third is X is not a subspace of R3. This is also false because we checked, or you will check as a homework, that these three conditions are met. Hence this is also incorrect. So the correct answer to this particular question is just A. Okay, fine. Now let's see the last question in this particular video. So we have two vector spaces, two finite dimensional subspaces of vector space V, which are W1 and W2. And the dimension of W1 and dimension of W2 is given, which is 8 and 6 respectively. The dimension of W1 plus W2 is given as 13. Then which of the following statement is or are correct? Okay. So first of all, with this information, what all can we do? So we know that dimension of W1 plus W2 should be equal to dimension of W1 plus dimension of W2 minus the dimension of W1 intersection W2. So if I know this, can I put the values and find the dimension of W1 intersection W2? I can, right? So this is a simple mathematical equation. You have to put the values. So this is 13 is equals to 8 plus 6 minus dimension of W1 intersection W2. Okay, so this is 14 minus 13, 1. Therefore, dimension of W1 intersection W2 is actually 1. Okay, now we have this information. Now let's see the options one by one and see which one of them is or are correct. W1 intersection W2 need not be a finite dimensional subspace of V. Okay, so first of all, this is incorrect, because if you are taking any two finite dimensional subspaces and then you are taking an intersection of that, it's always going to be a finite dimension. What is the meaning of finite dimension? It means that the dimension of the subspace is some finite number. It's not like infinity, right? So this is incorrect, because for any two finite dimensional subspaces, if you take the intersection, it is always going to be a finite dimensional subspace. So this is false. There exists a non-zero vector u such that Lu is in the W1 intersection W2. Lu is the set of all linear combinations of u. So this is saying that there is some non-zero vector u such that it belongs to W1 intersection W2 and all possible linear combinations of that vector also exist. So we know that the dimension of W1 intersection W2 is 1. It means that it is being spanned by a single vector. Correct? So it means that there is just one vector in the span of this particular vector space, which is the intersection of W1 and W2. It means that the dimension of this vector space is 1. So it means that the span is by one vector, the basis contains only one vector. So this actually is true, that there is a non-zero vector u such that it spans W1 intersection W2, because the dimension is 1. So we'll need just one vector to span this particular intersection of two subspaces. So this is correct. This is indeed true. Now let's look at the C option. There exists U1, U2 that belongs to W1 and W2 such that U1, U2 is a basis for W1 intersection W2. So if U1 and U2 belong to W1 and W2 and they are forming the basis of W1 and W2, then it means that U1 and U2 are linearly independent because they are in the basis, and W1, W2 has a dimension 2, which is incorrect because we just found out that the dimension of this subspace is 1. So this is false. Okay. Because the dimension of W1, W2 intersection is just 1. So the basis cannot have more than one vector. It will exactly have one vector in the basis. So this is false. So this is false, this is false. Now let's see the fourth option. Dimension of W1 intersection W2 must be between 5 and 7. So this is also incorrect because we find out the dimension of W1 and W2 is equal to 1. Okay. So the only option that is correct in this is B. So with this, I will end this video in which we have discussed so many questions on vector spaces and subspaces. We also covered linear independence, basis, dimension, and I'm hoping that now you have a better idea of how to solve these questions. So if you have liked this video, please share it with your friends also who are struggling with the same topic. Also, please let me know in the comments what other topics that you're struggling with. I will try to make a video on that. Particularly, I'll solve questions on that particular topic so that you'll be better prepared for GATE. Thanks for watching.